So for this last lecture, again, I went back to Arvin and I said what I should talk about. And we had a few options. And first, I thought I would do a little bit like what Amal did, which is let's come back to motivations a little bit. Now that we have told you about what we are doing with this whole, let's specify hardware, let's say what we're expecting from the machine, and let's prove that our actual implementation refines its specification. It's like, why are we actually doing that? How much does it matter? And by that, I mean, even just in terms of performance, how much does this little trick of computer architecture matter? And I wanted to present some work that is not by me at all, but it's a very important piece of work that not everyone has seen in the PL community. It's a piece of work that was, I think, published in 2017 or 2018 by Lausanne, Butler Lamson. I think there was also Joel Emmer, a bunch of other people basically across the river. That was named, there is plenty of room at the top. And the entire rationale was first, it was a pun on the famous Richard Feynman quotes that said there is plenty of room at the bottom in the, I think it was in the 60s or 70s, where he said, like, even if we do nothing, physicists are going to get better. They're going to make transistors smaller. And even if we are not smarter, computers are going to get much faster just by the mere fact that physics is getting smaller. And in 2017, basically, they said, actually, no, when you look at the computing stack, there is plenty of room at the top. There is a lot of bloats at all the layers. And they sort of went through the game of trying to identify and quantify how much is there at the language level, how much is there at the computer architecture level, how much is there at the algorithm level. And I want to talk a little bit about that to put things in perspective. And then I want to tell you a little bit about refinement maps, and actually just a little, how many people have done proof assistant stuff? I spent, let's say, more than 10 hours using a proof assistant. Okay, so maybe I will step through some code, but it seems like I will lose half of the room. We will see. And then, so you saw that I talked about refinements, the weak simulation, and the hard part was to find phi. And someone had sort of very good insight that very often in computer architecture, the kind of phi you need is like, if I were to wait for the machine to drain, wait for the instruction in flight to drain, then it should be the case that the machine, once there is nothing in flight, corresponds to the specification machine. And we can actually formalize that systematically, and that gives us a very good way to define phi relations and prove correctness by using those definitions without having to be creative about finding the phi. And then I want to talk about maybe, so Arvin told me you should talk about that, but it's sort of more of an idea that we have repeatedly hit the same problem. And the problem is that we want to be able to modularly decompose our system, and we want specification for the submodules. And it turns out that that's the problem. The problem is, even though you might have a specification for your top-level module, for your top-level machine, let's say you have a specification of your ISA, which is your processor plus your memory, it's actually very hard to write a specification just for the processor or even just for the memory. And I want to tell you a little bit about that because I think that's one of the problems that a lot of people are having, and not just in computer architecture. And I think that the solution we found for this very specific instance is kind of interesting. So the things that I first wanted to start with is this morning, and a bit yesterday, we discussed this simple example where you have a combinational G of F, and then you can split it in two and pipeline it. And it's sort of a rewrite, and you can prove that this is a valid refinement, and there is indeed a weak simulation of the left by the right. And actually, you can sort of see a lot of computer architecture tricks like this. If it's actually stateful, then you can say that when you have your things that is reading and writing from the state, you can sort of say, well, I can split it in two, but I need to add a little things to make sure that if I read after write dependency or write after write dependency, I stall. But basically, if I take care of this little extra dependency tracking mechanism, I can have a systematic pattern, a systematic way to refine a computation like this into something that is going to go faster because, again, I split the critical path between F and G. And sort of you can go over many architecture trick. One that is very, that I like a lot is that, let's say you have a module S, and this one is taking quite a little time to produce its output. Let's say it's a GCD module. I really like GCD modules. So it's a module where you send A and B, and it produces a GCD and A and B. But it takes a variable amount of time to produce the output of A and B. So what you can do is you can put two modules next to each other, and a little cue to remember, did I send to the left side or to the right side? And then you can prove that this machine, which has twice the throughput as this machine potentially, are also refining one another, okay? So basically you can sort of go over, banking also is one that you can show. It's a traditional architecture techniques. And we can sort of try to see if the programming patterns that we are using as computer architects can be isolated as a sort of local rewrites or local refinements. And then we could hope that we can potentially prove the correctness of compilers, of processes, simply by applying sort of the library of rewrites we have and get to our final processor. And you know, a lot of the things that we have been doing has basically been looking at the last 30 years of ISCA and micropapers and sort of saying, oh, can we do a refinement for those? Sometimes we sort of can, sometimes we sort of can't, and we basically do that, you know, very pedestrian way. So, you know, one of them is cache coherency, one of them is vectorization, and all that. But why all those things matter a great deal is that they give a ton of performance. And I like this picture from the papers, there's plenty of them at the top, which start from a little piece of information. They are trying to run a matrix multiply, 4096 by 4096, and they write a naive triple loop in Python. And then they say, okay, how long does it take to run that computation? They say, well, it takes some number of seconds. And if you look in absolute peak of performance, that is, if I open my processor, I look at how many adder I have and how many multiplier I have, the actual efficiency of my code is actually 0.00%. That is, I spent almost no time multiplying, spent almost no time adding, spent most of my time doing bloats, and almost no time doing that. So then they say, okay, let's rewrite, because you know people always say, and obviously Python is slow, so blah, 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 let's do it in Java. So they do it in Java, and then they write, you know, naive algorithm first, and they get, whoa, 11 speed up. Okay, that's something, okay. Then they say we are gonna rewrite it in C. You know, maybe today they would have done it in another safe language, but whatever. And then they get another 4x speed up. And what is interesting is not the fact that this is much faster, it's the fact that this is still ridiculously slow. Like you're at 3% of actual peak performance, even though you have written in supposedly the fastest language. So what is there to be gained from there? Well, the next thing they do is like, let's parallelize the algorithm. And I'm displaying this directly. And they just use, you know, the fact that you have multiple cores, and they get another 7x. Notice that the 7x they get is more than the 4x they got from going from Java to C. So the parallel loops gain a lot. And then you are roughly at, you know, 20% of, 0.24% of peak performance. Yes? Peak performance, you can think of it as speed of light. That is, if I look at, what's the fraction of speed of light? If I look at my hardware, it have, let's say, 10 multipliers. And I am intuitively bottlenecked by the number of multiplication I need to do, which is roughly 4096 cube, approximatively. And I'm thinking about every cycle, how often do I use all those multipliers? And if I never use any multipliers, it means that I am underusing my, computationally, that should be the bottleneck. But if it's not the bottleneck, it means that I'm spending time waiting for things to be able to feed my multiplier. Does it make sense? Unused part of the machine that should be the thing that should be used. In the case of matrix multiply, it's a multiply. And so they go on, and then they apply an algorithm technique, which is just divide and conquer. So you know, this is mixed programming language, then a little bit of concurrency and parallelism, then a bit of algorithm. Then they go with vectorization, and vectorization is a huge 3.5x speed up. And then they use AVX intrinsic, which is vectorization to be able to do load and stores, scatter gather with the instructions in vector instructions. And you see that basically this, and arguably this are sort of computer architecture techniques which you need to be able to exploit, because at the end, by the way, at the end you only still get 40% peak. That is, you still have a little bit of room. But you get a 62,000 speedups over. Yes, go.
Yeah, question on how to measure the fraction of peak performance, because the multiplier, for example, always multiply at every cycle. So how do we know that the multiplication that is doing is the one that is peak performance?
So you're saying that you could be doing more multiplication?
No, because we are doing some computation
No. So, okay. So that you're making a good point. So here, so what I said this morning was, in any case in your machine, because it's hardware and it's parallel, even when your machine does not run an addition, it actually implicitly it's feeding data to the adder and it's just throwing away its results. That's very different from when I have a concrete program and I know I need to do 6 billion multiplication. I do a back of the envelope. I'm really talking about spreadsheet computation here. If I have 10 multipliers and my computer goes at 5 gigahertz and I need to go and do my 1 billion multiply, then I can compute how long it should take at the minimum to be able to finish my computation. And then if I am very far from that, I'm saying, well, there's something that, I'm paying for control, I'm paying for something at another level. Does that make some sense? Yeah. So that's basically the conclusion from this little paper was that there is a lot to be gained. And actually, if you go to specialization, I did some measurement a while back, you get to a 1 million speedup. So if you use a TPU, for example, you get to a 1 million speedup. So, language do matter a great deal, but using the feature of the underlying architecture does matter a great deal, and making sure that the architecture is as efficient as it can be also matter a great deal for performance. Many people usually don't actually care about vectorization when they write code because they think it's sort of a niche thing, but for some computations, that's really important to be able to get good performance. Okay, so this was just a little bit of, I wanted to share that with you because I think it's good, it's counterintuitive, and I think that the quantitative aspect of it is good to have in mind. So now I want to go back to this simulation relation that I've discussed quite a little bit in the past few days. We have discussed that our first example was this little example, where we have this system which is f of g pipeline, and we have this system where there's just one queue, and we came up with this relation fairly manually to explain that indeed they are related to each other, and that inductively you can prove that for every step of my system 1, I can take a step in my system 2, and so on and so forth. Okay? Now, I wanted to actually spend a little bit of time show you that we can actually do that in a proof assistant. And the reason why I wanted to do that was because maybe it's very clear for some of you, but maybe it's not so clear for others, that a lot of the things that we are discussing really are naturally encoded in a proof assistant. That is, when you have those deduction rules, they look like math, but there is a very natural way to represent them in a proof assistant. And if you only have a sort of a little experience in proof assistant, it might be something that you don't know. It might be useful for you to learn. So I wrote the code ahead of time because I was a little bit scared that this would go, because proof assistants can go wrong. Okay, so I wanted to, instead of doing a full system, super complicated, where I have a DSL and I partially interpret this, I decided to just do a mass model of auto systems and to do the proof that the two mass models. Yes?
Can you make the font larger?
Yes, this should be possible. That being said, between this morning and now, there was an update to my machine, and it crashed code, and it's a known bug that no VS Code doesn't start without adding a special flag to it on Ubuntu. Okay, so our system has an interface, and in this case, the action methods are just an inductive type, where I have this enqueue method, and the dequeue method, where I enqueue an argument. And I define two types corresponding to the implementation type and the specification type, okay? So here I'm just doing an encoding of my problem. And then you remember that we have a notion of observation, and here I have an observation for my first system, which is the first method. And what it does, it simply states a relation between the state and the thing that is observed, and it's a partial relation, and it says, well, if it happened to be the case that the state contains something of the form I am and O appends the singleton E, then I can observe E on the output, right? So if the queue was empty, then I could not observe anything. It's a partial relation, okay? And that here, I really did the same things that I did on the board, except that it's more readable because it's on the computer. And I can do the same thing for the specification. And for the specification, in that case, it's very similar because I just have one queue and I just read from the last element of the last queue, okay? Okay, now what becomes a little bit interesting, first we need to define the notion of indistinguishability, which I like to call masquerading. And so I say that a specification can masquerade for an implementation if for all written values that I could observe in the implementation, I could also observe it in the specification. Please interrupt if there is any notation or things you are confused with, because you don't know yet about proof assistance. Okay, so now I want to describe the system. And the system that I have, first on my implementation side, contains 2 methods and 2 rules. And I can describe that simply as a relation describing the state transformation due to the methods and the state transformation due to the rules. So I can say, oh, oops, no, it's too big so you can't see the signature. Up. How do I do that? Okay, you imagine that there's a prop at the end. So the signature is basically, well, I want to pack it in one relation. What it means to go from one state to another state, I can go from a previous state to a next state by using a state transition corresponding to the rule do F or to the rule do G. And here I have 2 cases, I have one for do F and one for do G. And you see that I'm indexing the relation by the transitions that I'm taking, and that's a useful trick because whenever I'm going to have a state transition, I will be able to know where it's coming from because I will have the index of the transitions. Okay? And then I need to be able to say a sequence of transitions. This is very standard if you have ever done something in Coq, but you basically need to say, what can I go from one state to another state by a sequence of rules? I'm saying, well, a sequence of 0 rules, it just goes from itself to itself. And then I can do one more rule simply by, if I were able to go from one state to another state, and then I can add one more state, and I can go directly to the transitivity. Okay? Does it make sense for everyone that does some amount of proof assistance? Very straightforward. Okay? Now we need to define a new relations. I think what you want to, I want you to get away from this thing is that every time you talk about a relation, you think inductive proposition. It's a very good way to encode a lot of things. So same thing, I have a implementation step. I can just say, what does it mean to enqueue? Same kind of deal where I'm saying, well, if I am in some state and I want to enqueue a new element in my implementation, I just put it here and I say that I just enqueued. And I can dequeue only if there was something in the end, and then I remove it from the state. Okay, so extremely straightforward. And then I need to do the same thing for the spec, so I do the same thing, except that there's a little plot twist, because knowing my spec, there's no rules, and I'm directly doing the computation here, right? So all that leads you to be able to state a theorem. The theorem, first you need to state the simulation relation. In that case, I picked the simulation relation that someone suggested this morning, which is just, I break the implementation and specification state. The specification doesn't need to be broken much. And then I just say that mapping G of F on the first queue plus mapping G on the second queue plus mapping the third one is equal to, maybe I should wrap line here. Oh, it's very disturbing. Up. Let me actually try to indent that in a not completely awkward way. Okay. Okay, so this is all what we said this morning, and nothing went wrong, which is surprising because we are in a proof assistant. Well, so standard stuff, you need to write your little own tactics to clean up stuff. Sometimes you will have conjunctions and you want to make sure you break them apart. Sometimes you have existential, you want to destruct them. And sometimes you have hypotheses that are just cluttering your context because it's A equal A, and you want to get rid of them. And that's exactly what this little snippet does. And now I need to prove a few things, right? First, I need to prove that if I were to take a step in my implementation, I can take a step in my specification for the rules. And it happened to be the case that there is no rules in my specification. So the theorem is very simple. It derives into a degenerate case where I'm saying, if I was related and I were to take one step to a new I prime, then it must be the case that this new I prime is still related to the same value because there was no step I could have taken in my specification because there is no rule in my specification. Does it make sense? And then I can go and prove that theorem. We can delete that. Do we want to delete that? We want to delete that. Up. So it's just to give you a little sense of what it feels like. So what should we do? Yeah? Why? Because that's always the beginning of your proof. Okay. And let's give a little name to that one, maybe phi, okay. Then what else do we do? We keep introing. Let's intro everything. You're suggesting to intro everything? Okay, let's intro everything. What do I do next? Here R is the kind of rules we are doing. Is it F or G? And then we have an hypothesis that we've stepped by R from I to I prime. And we have the hypothesis that we started being related in phi. I could, if you want, I can unfold phi this way, it might be clearer, but I'm not sure that it's going to be, it might clutter a little bit the context in star. Okay. Okay? So what should I do? Yes? So we might want to do an induction transition. But so on which one actually? On what? On the rule implementation? But I don't think that there is an inductive case. Well, are you suggesting do induction? I mean, we can try. Induction on what? H0 or? That's a good guess. I mean, as good guess as any, but there's a little. Do we have inversion here? What do you want to invert? Okay. Okay, so I think that the first thing you need to do is to say, well, there are two cases. There is a case where I'm doing the rule number 1 and a case where I do the rule number 2. So I need to do case. I need to say, okay, there are two cases. And for some reason, I should do destruct instead of case, because as you saw, well, that's exactly what I think about proof assistant. Look at this. This is cool. So you do case, and it doesn't actually do case because it doesn't replace the value of R by do F and do G. But if you slightly make it different by doing destruct, which is a variation of case, then it works. Okay, so now we have two cases. And now we can do an inversion. We can do an inversion because if we know that we have a step from I to I prime, which is of the form do F, then it gives us much more structure on I and I prime, because it must be the case that I contains something in the first queue, and it must be the case that it produced something in I prime later. So I can do inversion on H0, and then it gives us exactly what we want, which is, well, it must be the case that I contains something there, and then I prime pushed that thing with composing with F into the next step, right? So I do inversion, and then I substitute the equation that I obtained, and then I get into that situation. What do I need to do next? Does it look like the problem is solved or not quite yet? No? Yes? Simple in star. That's sort of when you're desperate. You're like, and then you're like, oops. Okay? I mean, I'm good with that. Well, I think we can clear H0, right? We just inverted it. So there is nothing it can give us anymore.
I can't tell, does H match? We can rewrite from H, I think.
Yeah, I think there's a way to get from H to do that, but it's not quite there yet.
Yeah, okay, so the first thing is that you see that there is a little b in jail under the map here, right? So we need to get these little things back up, and that happened to be a lemma, which is probably called something like map ASOC. No, map append. That's also second part of doing. No? Map app map. Okay, and then it's complaining because it's in H. Yay, it worked. Okay, and then it almost works. Why is it not working? And so the people that have never done proof assistance are probably thinking, what the hell? Because the things are not matching, and why is it not matching? So what I can do is replace the S here by the S here by doing a rewrite in the other direction. This way it will be even more obvious that it's frustrating. Okay?
Can we simplify? Because I think we can simplify the map on B.
Okay, so we simp. Okay.
One of the stronger tactics could probably solve it from here.
Okay, what would you want? What do you want me to type? So usually at that stage you go and you say first order. Oh no, and then you go E-auto. Oh no. Okay, but let's do it the pedestrian way because that's reliable.
I think we can do something with the cons and maps.
Yeah, so here the problem is the fact that, you know, there is no magic A plus plus B plus plus C is not the same thing as A plus plus B plus plus C.
Yeah, there is. There's episode.
Yeah, there's a lot of episodes.
Sorry?
That's episode.
No, but I mean, I need to do a rewrite.
Oh, yes.
It's not definitionally equal, right? So I do rewrites, and then what is the name of this thing? It's called AppAssoc, I think. And then it did something which looks reasonable. Does it?
Yeah.
And, or maybe we can actually do it in the opposite direction. So at that point, usually you start banging on your keyboard until it works. Yes, that was a good one. Hey, we won. We want the pleasure of saying that it's trivial. Okay, and then we can do the other one. It's very similar. So we just bang. We always have hope when we are doing proofs. So, yay! We just did a proof of a very elementary fact. Okay, so we need to do the same thing for the other one, and actually we could do it. Let's not redo it because it's just painful. But it just goes through. It's fairly straightforward, and then we have proven our thing. And then we need to prove that phi is implying that you indeed have this masquerading business where indistinguishability. And that one is even simpler because if you just sort of reduce, it just goes through. Okay? So that was just an example to show you that if you can come up with the phi refinement map, then usually the question is just how much time you're going to lose writing those lines of code. But eventually, with enough time lost, you will succeed in proving your theorem. And you can spend a lot of time, you know, writing automations to make sure that you don't have to do that too manually. And you can go a long way with these kind of things, and it works great. The problem is the fact that the first premise of that thing is you were able to write the phi refinement map. And you see that here, the system was simple enough that it was not too bad to write the refinement map. But if, for example, I had states, oh no. If I had states, it would have been much trickier to write a refinement map. Actually, how hard it is to write phi, even for small design, it can really easily be pretty hard. And in some situations, you need things that are even more painful, like things called prophecy variables. How big is phi? Well, you know, even for small design, it quickly becomes too big. And you know, I have example of even the small processors and what we wrote this morning. If we were to write a small processor, and then we do the skip optimization of skipping directly from execute back to fetch in the case where it's not the memory instructions, then you start getting into 50 lines of refinements. And every time you change your design even a tiny bit, you need to go over the proof again. And that's really going back to what the fellow was saying yesterday, of a really big problem of when you're doing this kind of stuff is that you feel desperate every time your advisor asks you to change a thing in the design. Because you need to redo the proof, and it takes a lot of time, and then it doesn't feel like you're doing anything new anymore. It just feels like you're basically retweaking the proof to be able to match and, you know, renaming H0 into H1. Okay, so what I want to talk about is sort of a way in which you can actually write a fairly good phi without having a fairly good simulation relation. And actually, it's a sort of revamping of a 1994 idea. So in 1994, there was a paper at CAV where Birch and Deal were sort of concerned about a slightly different problem. At the time, there was no notion of interface in hardware, and they were trying to define the notion of correctness. So they were trying even just to see what the hell does it mean that my processor is correct, right? That was the question. And they came up with that idea where they said, actually, it should be the case that the correctness is defined as being, it should commute with flushing. What it means is that if I have, this is a pretty diagram, I think. If I have my implementation state, and I flush the machine, which is something that is not very well defined in the paper, but intuitively you say, I just wait for all the instructions in flight, I stop fetching, stop the spigot, then I wait for all the things to drain. They said, if I were to do that, then I basically have a piece of state which is very easy to map to my actual specification, because my actual specification have only one instruction in flight, so they map very naturally. And then they say that if I were to take one step in that world and then flush again, it must be the case that the diagram commute and that I could have just done one instructions in my specification and found the same result, okay? And they just said, we think this is a good correctness criteria, which when that correctness criteria hold, basically it means that your design is correct, okay? So the problem is a few things that we like and a few things that we don't like. The thing that we like is the fact that we see intuitively that it's very hard to write a machine where this property holds, but the machine is broken. Broken in the intuitive sense of it doesn't do what you want to do. So, you know, when people try to think about, like, at the time especially, the people, when you propose the definition of correctness, what they try to do was to break it, right? You know, can I write a machine in which the property is true, but I don't want to be able to say that those two machines are equivalent to each other or that they are equivalent. And so this is very hard to actually get to that kind of thing. There is one way with sort of saying if you have a machine, that's actually a cool machine. If I have a machine in which my processor is doing that. So I have my specification, and let's say for the sake of argument, then my specification in this morning processor. So you know, you remember I have this fetch, decode, execute, write back machine. And what I'm going to do in my very sophisticated implementation is that I'm going to keep the same state, register file, PC, and memory, but I'm not going to do anything with it. I'm just going to add a counter, which is just going to count the number of things that I should do in the future. And then what I'm going to say is that in that diagram, what happened when I do a step of my implementation, I just bump that counter. And I just say, my machine, the only thing that it knows what to do is to bump a counter by 1. Okay? But then what I say is that I define flushing as being, well, I'm just going to very quickly apply all the things that I should have done, but I was too lazy to do. And then I'm obviously going to refine the state of my specification, because I can just do it in the virtual world of flushing. So you can basically write this very awkward machine in which the machine doesn't compute anything. It just keeps a counter saying that if I'm being asked where I am, I know where I am, and I know how to reach the state where I am in the shadow logic, so in the flushing world, to be able to prove that it's actually, I'm still matching on the specification. So I don't know if that is clear. It's a little bit of a counter example, sort of an adversarial example. So if you are not so familiar with architecture, it might look a little bit weird, but you know, we could formalize that and basically show that we can write this very awkward machine that is just made of a counter and that implements a processor, even though it didn't do any instructions. So okay, we are not super happy with that. But what was very successful is that architects loved it because it meant something. You know, it was not just a formula. It was like intuitively it made sense to them. And so this was a successful thing. And in the case where you have a finite bounded pipeline, it was also a very successful criteria because you can check that criteria with model checking. And if the pipeline is like of depth 3, 4, or 5, then you can basically completely prove the correctness of your design with zero amount of effort. You don't need to do any manual proof for that. Okay, the thing that is problematic with that definition is the fact that this correctness definition basically depends on how you define the shadow logic. How do you define the flushing? You know, here I can have an arbitrary function, and basically the notion of correctness is relative to the notion of flushing. And then people realize that actually you might be able to flush in different ways, and there is not a unique definition of correctness. That is not so good. And also you can actually get it wrong when you define flushing, and then you don't flush, and then what the hell, you don't know what you're proving correct, because you just have a notion of correctness that is relative to a definition that is broken, okay? So what we thought was to think, okay, but we can formally define flushing. We can formally define flushing as an inductive relation in which we are going to say, well, you know, there's an easy case. So easy case is I know how to relate my implementation and my specification in the case where there is nothing in sight. So for all L, if I have nothing in the first two queues, I know to relate the two, the relation is completely straightforward, okay? But then I'm going to say, well, you know, if I knew that I was related at some state I prime, and I could reach that state I prime from some I by doing one step of do f, then it must be the case that I was flushable before, because flushing is emptying the pipeline. So you can go backward, and you can say, I can inductively define what it means to flush by saying, well, if I were flushable one step forward, then one step backward, I must have been flushable, because that's what it means to be flushable, is to empty the pipeline. So you can sort of, instead of having to do what the fellow suggested yesterday, of saying, conceptually I can push the thing on the right, you can have the proof assistant pushing the thing on the right, defining the relation to be the closure of basically looking at you are flushed, and then what are all the antecedents, all the previous states that would have led to that flush state, and you look at the closure of that relation, the smallest relation that verifies this set of inductive relations, and then you have basically described implicitly that thing's flushed. Okay? And now we can, so intuitively, we have just defined what Birch and Deal said, right? We have basically defined the Birch and Deal criteria in a proof assistant, but now instead of using it as the correctness criteria, we are using it as the simulation relation. That is, if we got it wrong, we won't be able to prove it, because we won't be able to prove that it's inductive, or we won't be able to prove that it implies a form of indistinguishability. Okay? And so, why is that the case that this definition is good? This definition is good because it's an inductive definition, and inductive definitions are good. That's something that you probably have gathered. And why are they good? They are good because you can do a proof by induction over the derivation of that expression. Okay? So now let me just add one more thing. When you have such an inductive file like this, I want to. This is syntactic sugar for this. All right. And I just want to write it because I think I figured that out way too late in the PhD. Fairly obvious, but up. And I won't do the last one. But when you have a judgment rule that you write, whatever the judgment rule is, you can always inductive, and especially if it's well-formed, you can encode it as an inductive proposition in Coq. And the translation is fairly straightforward. You just add as many little arguments that you have in your relation. So if you have a typing relation, you might add a gamma, you might add a few more extra parameters in your definitions. But once you have defined all of them, then basically every single case of your deductive system corresponds to one case of your inductive proposition, and it's completely straightforward. So that's why people are, when you define a set of inference rule, you really are defining something that is completely straightforward to encode in a proof assistant, and so you have no excuse to not actually do it and then prove things in the proof assistant. Yes? No, do f means I just want to transform, take the head token here, apply f, push it here. Yeah. And do g means that I want to take a token here, apply g, and push it here.
That's only one.
Only one step, yeah. So basically, if I look at the closure of that relation, the smallest relation closed under the three constructors, it is describing all the states that are flushing to the same relation. Yes? Yes, so there is positivity criteria. So you cannot, you could define types that you would be able to prove that they are false if they happen on the left side of an arrow. I don't want to get too much into details, but yes, I do have reference. Probably software foundations, and if not software foundations, certified programming of dependent type by my advisor, Adam Cipolla. And I think the problem is always that I think that there are types that you should legally be able to do, but you can't do because the criteria is a little bit too strong compared to what you want. So there's always this sort of discussions about, is it that we are enforcing too strong of simple criteria, and we could do better if we could have a more semantic view of the object. Okay, so, but that I think I just wanted to briefly describe because it's very important. So now, similarly to what we have done, what Frank has done, it's like when you want to do a proof and you have a phi in your context, you know you will do an induction over the derivation of the phi, because now you have a natural induction hypothesis that tells you that it was true for the subtrees of the derivation, and it's going to be not too bad to piece that together. And that's what I want to do right now. Okay. So the theorem is a little bit scary, but it's not too bad. So what we have is we have the fact that we want to prove that if we have phi, then I think it's the same theorem that we proved just before. For all step R, if we were to be able to go from I by R to I prime, then it must be the case then phi of I prime and S, right? This is the same statement that I proved 2 minutes ago for the custom phi, which was explicit, the one that I had here. Yes, there's a for all that's missing, but for all R, for all I, for all S, then if I can step, then it's necessarily the case that I'm still related after I step, okay? And the fact that this definition now is differently defined doesn't matter. So in the previous proof, you saw someone suggested to do the proof by induction, but we didn't do the proof induction, we did the proof by case. But now we should do the proof by induction because we have something to induct over, which is the phi, okay? So we have these statements, and obviously the first thing we want to do is, well, do an induction over that one. So if we call that H, then we want to do an induction over H. Okay, so now what is going to be the base case? So do I still have the definition somewhere? No, I erased it. Up. Okay, so in the case where of the first step, our hypothesis H necessarily is in the special form where it is phi of empty L for some L and L. Okay? And we want to prove that for all steps that we would take from that state, that is, if I start from an empty thing and I take a steps, which is going to be, let's say, an R step, I'm going to end up in a new state, LBC, and it must be the case that I'm still related to L in that LBC. Why is it clearly true?
Because both R steps won't change your state.
Actually, you can't take R steps, right?
Oh.
Because this one is empty, so I cannot pull from that one, and I cannot pull from that one either. So this case is straightforward because absurd. Does it make sense for everyone? Okay. Now, what about the inductive cases? Okay. So, by the way, this is the proof for all rules. We will have to do. When you get through a proof and it feels like this, it feels there is something wrong. Why is there something wrong? Because there is only absurdity in the base case. That should feel wrong somewhere. It's like, no, there should be something that does something in the proof in the base case. The reason why here there is nothing happening in the base case is because there is another theorem we have to prove, which is that for every action method, it's also true that the steps happen in the action method. And so there would be things happening in that base case, not in this one, okay? So base case is good. Now let's go with the inductive case. Okay, and this one is tricky. So what does the inductive case tell me? We have two inductive cases, fair enough. So let's start with one of them. For example, do F. What does the do F case tell me? This is tricky. It's basically a question of how do you generate the inductive principle from the definition, and it always creates little knots in your head because you don't necessarily know what it looks like. Okay, so it must tell me that I knew the theorem that I'm trying to prove on a smaller thing, okay? And I knew the theorem on this one, which is on I prime and S. That's basically what it means to have an inductive definition. And what was the theorem? The theorem was telling me something like this at the top. It was telling me, so my hypothesis in my context, I must have an hypothesis which is called the inductive hypothesis. And what does that hypothesis say? It says that if, I think that's what it says, it were true there, then it must have been the case that the theorem held here. Oh, I have a fall here as well, so I need to be a little bit careful with that. If someone can make sure I'm not making mistakes, it would be good. Now, so for all I second, implies phi of I. What did I do? Did I do something wrong? No, that's good. So, one sec. For I second. Does that look reasonable? Yes?
Maybe I'm missing something, but wouldn't the I second go in the hypothesis and not the conclusion? Like, are we inductively assuming that phi I prime x is true?
So what? Okay, let me do a diagram because I need my diagram to be able to figure that out. Yeah. So my diagram is the following. My diagram is basically the diagram that we had on the thing, which was if I have a pair, if I am relating I to some, it's going to be a 3D diagram, to some S. And then I know that on that state, my theorem is true, that if I were to be able to do one step forward, then I can do one step forward and still be related. Let's call it I prime, S prime. Then I want to prove that assuming that thing, if I were to pull back one step before, so let's call that, let's reuse our naming scheme. So this is I north, this is so hard, I north west, I prime, I south east, and S north east, and S south east. And then what we want to prove is, assuming we have that, we can prove that we can lower that one, and that this one is related to the one. So I north, southwest. And there exist steps in my specifications, which are basically here, such that this one relates to this one. Sorry. Okay? And how do I do that? I'm basically going to need to use my inductive hypothesis. How am I going to use my inductive hypothesis? I'm going to say, well, there's 4 cases. Either that step was a do F, or that step was a do G, and either that step is a do F, or that step is a do G. Okay? But the trick is the fact that do F and do G commutes. You can prove that if you can do F and do G, then you have the following commutative diagram. That is, if you were to do F and do G, then necessarily you can do F after do G, and you can do G after do F, and you end up in the same state. And that's something that you can just check very simply because they are working on independent token, so they commute. Okay? So in the case where you have do F on both sides, the theorem is completely straightforward. Why is it straightforward? Because if you do F here, it's the same do F that you were to do here. So the theorem that you're trying to prove is exactly your inductive hypothesis. You have nothing to do. So if your step here and your step here are equal, then the proof has no content. And if the step here and the step here are not equal, then what you need to do is you need to say, well, they happen to be commuting. So I know that the theorem is true here. And then I can use the constructor of the phi relation, which is going to be the 1 more g, to be able to pull back that thing to that level. Okay? So I think maybe I should have done that on the proof assistant, but I was scared that it would scare you away. Because it creates a little bit of bloat when you do it in the proof assistant. But that's the key technique there is the fact that you don't have to think about the way you wrote that relation. It was completely described structurally from your original program. I didn't have any amount of insight. I just took all the rules one by one, and I added the backward relation for that rules. And then if it happened to be the case that my system has this nice commuting property, then just the proof is going to go through. And I can prove inductively by induction on phi. Then phi is inductive forward, and then I'm happy with that. Does that make some sense? I think that this was a little bit messy, but if you want to spend the time to do it more cleanly, we can discuss it. Or I can also give you proof assistant code to do it properly. Okay, so I actually had a bunch of slides to do that, but I'm not sure it was much cleaner, as you can see. Yes. And then, we still have to prove that phi implies indistinguishability. And that's actually not completely trivial. And there is some small subtleties that I don't want to spend time to do, but it can be done. Okay, so what's very good about this approach is that writing phi is not difficult. It's actually, you could just do it automatically. You could write a program that writes the phi for you. And if it happened to be the case that your processor is indeed Bourgeat correct, then necessarily this is going to be enough to do your proof. And then the only case that could be wrong is if it happened to be the case that actually your machine is not Bourgeat correct, which is in itself something interesting to know about. So it's like even if you lose, you won something. It's kind of cool. How big is phi? Well, it's only linear in the number of rules in the system. So when you have, typically when you do hierarchical proofs, you have rarely more than 10 conditions on the system that you're currently working on. And the subsystem has been replaced by their specification. So there is no rules in the subsystem typically. So that's not too bad. You don't need to change phi when you change the design because you just need to say, well, maybe I change one rule, but the inductive case doesn't change at all. Nothing changed in phi. The scam is the fact that there is n square case to consider, and that 10 square is a big number. And proof assistants really have trouble to handle such number of cases systematically. Okay? So that's the first thing that I wanted to tell you, that really when you want to figure out a weak simulation, this Bourgeat idea, you can formalize it very naively and nicely, and it works quite well in proof assistants. And this applies outside of, when I talked to some folks about that technique, they said, oh yes, maybe it could be used for CRDTs, like, those conflict replicating data types, those fancy data types which have some difficulty to be proven. And there are a lot of situations in which you have many things in flight and eventually things should be working. And when eventually things should be working, one good way to describe that is inductively. You start from the case where they are working, and then you go backward, and then you do structural induction on the relation that says that eventually they should be working. And so I think that's a good idea to keep in mind. So I want to finish in the last 10, 15 minutes, I'm not sure, by a little explanation of what's actually one of the main problem and what we are facing all the time when we want to do proofs. Because same thing, I think that even if you do software verification, you would face a similar kind of problem. And it's good to know that there are tricks you can play to work around those problems. So let's say that I have two systems. I have an implementation system and a specification system. And same thing as I was doing this morning, I want to prove a refinement between them. And conceptually, I have basically the MMIO queues that this morning we didn't do explicitly. We used external, we used display and stuff. But I could have pushed on two queues. And then that's basically the model of the system. And let's say that I just want to say I want to refine my processor. I have a simple specification for my processor, which is the one that we wrote, the fetch, decode, execute. I don't know if it's still there. No, it's not there anymore. The 4-cycle processor. And that's a very good specification. It's super simple to audit. It's less than 100 lines of code, so that's good. And I have a more fancy implementation, let's say a pipeline machine, and I would like to prove that correct. And what I would like to be able to do is to say, I don't need to care about memory. I want to prove the thing that is a processor in isolation, because if I ever change the memory, maybe I put a cache instead of that, I don't want to have to redo my proof for the new systems. So you want to be able to do modular proof. The problem is that it doesn't work. It doesn't work because actually the theorem is false. The theorem is false because in many situations, even though the full system might imply a weak simulation, the subsystem will typically not have a weak simulation. And I want to give you a very quick intuition for why. Let's consider the case of our processors that we did this morning. In the processors that we did this morning, we can guarantee the invariance that if I look at the trace of the the requests that are sent to the memory for instructions, then I never sent 2 requests back to back if I didn't get the response before. Right? There is always this invariance that if I do a mem.request, then I will necessarily call the response in my trace of events before I ever ask for a new thing again. Because remember, it's a state machine, so if I am in fetch, I'm not going to go back in fetch until I have went to decode, which is going to consume the thing. Okay? So if I look at the... Again, why does it not want to stay here?
No, it does that.
It doesn't, okay. So if I think about the right-hand side machine, which is this fetch, decode, execute, write back, I can guarantee and I can prove that I will never have, for example, as a trace in my sequence, 2 enqueue methods that are requesting a new instruction from memory. But that's exactly what I absolutely want to do in my implementation, because the first thing that pipelining does is precisely to send back-to-back requests to memory for new instructions without knowing what the next instructions. So I have a problem that is my specification is not a specification for my implementation. It is if I look at the full system and I forget and I inject memory and I inline memory, but it is not if I cut it at the memory boundaries and I look at the trace at the memory level. And why is it the case? It's basically intuitively because the loads that I'm sending don't matter as far as the MMIO trace goes. Because as far as the MMIO trace goes, I never sent back-to-back MMIO trace in both machines, but I still send things on the instruction memory. Okay, so I want to, this is a very simple case, right? You know, in my implementation, I can send back-to-back 2 requests. I will never see that in my specification, so we don't have a specification for a processor. And that's kind of a little bit provocative because, you know, there have been ISA specifications for a long time, but ISA specifications are not processor specification. They are processor plus memory specification. And they do not specify the set of load and stores that you can see on the bus when you're looking at microscope and looking at the machine. Okay, so how do we solve the problem? And that's what I think can be useful for several of you. The trick is basically to generalize the specification. The trick is to say, okay, my theorem is false, so let's make it true. How do you make a theorem true? You have something is included in something else, but it's not included. Either you make the left-hand side smaller, or you make the right-hand side bigger. And we don't want to stem the implementation any different because the implementation is what we want to prove. So you have only one solution, is to make the specification bigger. So for 1 minute, we are going to take a step back and say, okay, actually our specification was wrong. So let's rewrite our specification and say that actually makes the theorem true. And what can I do? I can say, actually in my specification, I'm going to skip my little machine, but I'm on top of that going to add just arbitrary load at any point in time to the main memory. And what's the intuition for that? It's like loads don't matter, right? When you do a load in your computer, it doesn't have any effect. I mean, it does have effect for security reasons, but as far as semantics goes, it doesn't change the state of the machine. So I can say, well, you know, basically my microarchitecture, I should think of it as a machine that can at any time decide to, on its own, emit a load to some address. And if I generalize my specification that way, that is, if I say that my specification is not just a 4-cycle machine, but it's a 4-cycle machine plus a random machine that keeps emitting load at any point in time, then my theorem becomes kind of true. I mean, it even becomes true. So the architectural intuition is the fact that some load speculation techniques can be completely wild. So instead of trying to model exactly what they do, let's be even wilder and say you can do whatever you want. Independently of the load you send, anyway your machine is going to be correct. So we take a step back and we say we generalize the specification and we allow arbitrary load. And we can actually formalize that, right? We can basically have one machine, compose it with a machine that generates random loads, and then join them somehow. Yes?
So do these loads appear on the trace now?
Yes, they do. That's the whole point, right? No, in my specification machine, basically, if my implementation was emitting back-to-back two load, which before I could never fake in my spec. No, I can fake them because when I have two back-to-back requests which are load, I can just say, well, the first one or the second one is basically was emitted by my nonsense machine that was just sitting there. Okay? That's a very good question. Okay, so the thing is that, okay, you just cheated, right? I basically had a machine, I had a spec, and I just made up a new spec. But I could have said anything. For example, I could have taken as a spec the machines that generate an arbitrary set of traces, and then my theorem would have been very easy to prove. And clearly, my theorem would not have said the things that I wanted to say. So intuitively, for example, if I had said my specification can emit random stores, this would have not been what I want to say. So why is it the case that it's okay, intuitively, to say that random loads are okay, but not random stores? And you can formalize that very easily by realizing that it's not that load don't matter, it's that load don't matter from the perspective of the MMIO trace of the full system. What it means is that I can prove another theorem, and the other theorem is the fact that if I were to put my generalized specification inside a processor, a full system where there is a memory, then from this perspective, the set of traces of MMIO traces that I would have here is a subset of the traces that I would have in the original machine that never sent this random load to main memory. Okay? And that's really one of the key insights of this notion of generalization is the fact that sometimes you can generalize the spec of your submodule because even when it's generalized, it doesn't cause harm in your full system, this extra load you have emitted or this extra element that you have emitted. So in this situation, I might have my generalized spec machine that keeps sending loads to my instruction memory, and I don't care at all about it because those are not the ones that are going to be going to MMIO request. And so those ones, I'm not going to create any new trace at the MMIO boundary compared to my original machine. Okay? So if I can prove that, then I have a strategy to do my proof. The strategy is first, I'm going to prove that my pipeline processor refined my generalized specification. Then I'm going to prove, note that this theorem does not mention the memory. So if I have a new memory subsystem, my proof is unchanged. Then I apply the refinement theorem, which I noted, I wanted to do little quick things on notation. So on the second lecture, I used the notation m square brackets of n. What I meant by that is that I have a parent submodule, which have a hole in it, which is typically the hole here. And in this case, I plug it with n, where n here would be the blue thing. And the refinement theorem tells me that at the language level, I can guarantee that this is refining m of n prime if I knew that n refined m prime. Okay? So this is a visual representation of the refinement theorem. And notice the refinement theorem, the premises talk about traces on the submodule, and the conclusion talk about traces on the bigger module. Okay? So, and once I have that, and I compose that with my proofs that those extra loads don't matter, then I just need to prove that, and I have my top-level theorem statements by transitivity. Okay? So that's basically a lot of the things that we have been doing in the past few months, and I wanted to finish a little bit with, if I can find the proof. Okay. So you could actually do the proof. I started doing at noon, but I didn't finish, so I just wanted to show you the beginning of the proof. So we can define phi prime inductively. Then we can try to prove the same theorem. No, it's by induction on phi. So now we have the base case, and the base case is absurd, so it goes through very quickly. And then we have the inductive case, and what I was struggling to write before nicely is generated by Coq for me now. And so I could basically say, okay, how do I prove that? So. And we could go on and on with that. And I don't know if I want to finish that today. But I actually have done it. Let me open it here. Okay, so in this case, I've rewritten the system in a slightly different way. So sometimes I put 2 queues on the right-hand side, sometimes 1 queue, doesn't matter, it's all equivalent. Then you can write your inductive phi. So that's what was written here. And then you can do your proof by induction that indeed phi is preserved forward. So here I did an explicit split. That there are 2 things I need to prove. That it's the case that if I step by f, then the theorem stay 2, and if I step by g, the theorem stay 2. You do by induction, boom, boom, boom. You do by case analysis, and you basically have 4 cases to consider because there's 2 square cases, and it actually goes through, and then the proof goes. Okay. So it really at this step you just bang on your keyboard until it tells you QED. Okay. Okay, so that's basically all I wanted to talk to you about today. And now, if you have any questions, I'm happy to take questions for the last few minutes. Yes?
How hard is it to come up with a generalized spec?
Very hard, yes. So that's a very good question. How hard it is to come to generalized spec? And actually, the spec that I just showed you that emit random load is not quite general enough for all the computer architecture optimization that you might want to do. But it's actually an activity that is easy to not snipe computer architects to do. That is, in many situations, that forces you to think about what you can ever want to do in the future in your machine. You know, very often you don't want to actually have a description of what your machine is doing right now. You want a description of what your machine could do in the future if you were to keep doing optimization on it. So it forces you to basically say, what is sort of an upper bound of all the behaviors that I ever want to allow you to have? And a very good example of that is if you look at this generalized specification for load, that's very general, right? I'm basically saying you can speculate any loads to any address at any time, and that's still going to be guaranteed to be correct to do that. But you could basically say, another thing you could say is like when you have 2 stores, and that's not what the spec doesn't do that, you could say, actually, my microarchitecture is allowed to squash store. That is, it's a very common trick. So there is a thing called a store queue and a store buffer. And in computer architecture, what you typically do is that if you have 2 stores back to the same address, you don't send 2 stores to memory. If you have store to address A and then to location value 1 and then store to address A and value 2, then you say, well, the microarchitecture can sort of collapse that and rewrite it into a store A2 because, yeah, you know, it's equivalent, right? But when you do that, it means that this behavior you would never be able to see in your specification. So now in your generalized specification, you need to be able to generate those kind of behavior as well. So in actually the full generalized specification that we have, it's basically a machine that generates the real program load and stores, a machine that generates random load, and then a machine that is a load store, a store buffer and a load queue, which is collapsing the stores to the same address and doing load to store forwarding. So if you have another optimization that you can do very often is if you have a store to an address A and then you have a load to an address A, you don't need to send that load because you know that the thing is going to return 1. So you will never see that on the trace. Okay? So what we found interesting with Arvin was the fact that when you're thinking about trying to specify what are all the possible sequence of load and stores that your processor can emit, you are implicitly describing a memory model. But usually memory model people are not thinking about it like this, but that's what you are doing. So one of the questions that we have asked, we have wondered about and we have sort of proven, is what is the memory models that we have described once you had a random load machine? And it's kind of interesting because it's between TSO and ARM memory model. So you know, that's sort of a beast that you describe and you say, here is my beast. And do you like it or not? I don't know. But yes, it's very hard. And when very often you really need to think broad, and you need to make sure that you're not just encoding one optimization. So that's a typical problem. Yes. Yes.
So two questions, but number one, like, how do you keep the proof in sync with your implementation? And two, it seems like you're writing stuff in your spec and improving.
Yeah. How does that work?
And also, well, more of my question was like, you know, there's stuff like Haskell or whatever. Like you can talk like, could you extract from the spec?
Yes. So we have worked in both directions, and you know it's basically depending on how I feel the day. We have tools that goes from Coq to BlueSpec and tools that goes from BlueSpec to Coq. So, and obviously never with the full language. So we have an entire pipeline that is completely in Coq. And actually we have a proven compiler that is in Coq for a very small subset of BlueSpec. So such that if you prove a theorem in Coq, you never talk about BlueSpec. It's all in Coq. And then you lower that down to a Verilog in Coq. And then you have your theorem preservation going all the way down to your RTL. So that's basically what I would say is the sort of like, let's ignore reality and let's do our own thing on our side of the world and let's just ignore what other people are doing. But that has a good story of trust, right? You know, you don't trust anything, you don't trust the compiler, you don't trust, everything has been proved. So that's the sort of, you write everything in a Coq EDSL, and then you have a Coq compiler, in Coq you have a compiler that is proven correct, and that lowers down to an RTL representation in Coq, and you also do a proof about that thing in Coq, and then you have a lowering of that proof to the RTL. Okay, so that's one way in which you can do things, but it's sort of negating the reality that you know, there's been roughly 20 years of optimization happening in the BlueSpec compiler, and you can do some amount of things in Coq, but you know, it takes time and it might not be the best use of your time. So there is another strategy. There's actually two other strategies. The first one is to say, I'm not going to compile that to RTL. I'm going to what's called extract it. So extraction to BlueSpec, to BSV. And that's just a pretty printer. And because the language is a subset of BlueSpec, it's fairly straightforward to extract. I mean, in practice, there's a lot of problem because we only deal with functional correctness. We don't deal with liveness. And so it's extremely common that you extract your code and then it deadlocks because, I mean, live locks because you have a liveness property. But I think it's true that we never had a bug in the proven code, except that the thing doesn't do anything, which is not a bug. And by our definition of bug. And then we have a completely different pipeline, which goes from BlueSpec, and that's fairly recent, and extracts sort of a representation of the transition system within Lean, actually. And that's actually something that I wanted to show you, but I completely forgot. Not that specific thing, but something related. And you know, at some point I told you that the compiler was basically lowering everything to lambda calculus. And there is actually a way to look at what the lambda calculus look like. So, and there's a way to look at the, and that's going to be, so if you call the compiler with the flag lambda ddump lambda calculus, then it pretty prints the intermediate representation of all the transitions internally as a lambda term. And here, if I could click, okay, and you see that now I have BlueSpec printed a lambda term, which is a function from the state of the module to a guard, which is when that rule can happen or not, and then the new state of the module. And then it tells me, well, you know, it's a lambda, and then it does a bunch of things, and there are primitives and stuff. And it's actually, this example is quite a good example because this is about 150, this is the processor we wrote this morning. It's about 150 lines of code because we have 32 registers, and basically every time you touch one of those registers, you have 32 cases. And so that's a good example where the first thing you would need to do if you wanted to prove that design would be to remove the register file, to replace it with a specification, which is a function from a fin32 value, because then you would not have this stupid case analysis on those 32 things, and then your proof would be much faster and much better. So it's a good example of modularity. So we have a tool ongoing where when you add -ddump lean in a fork of BlueSpec compiler, it spit out some lean for you, and then you can use that to be able to do proofs on your BlueSpec code. But it supports a fairly small subset of the language. There was another question, I think? That was the same question, okay. Yeah, so in practice, most of the designs that we do that are published in Computer Architecture Conference are not proven. We are just doing pure BlueSpec stuff, and it's sort of, there's still a lot of features that we don't support in those tools to be able to be fully useful for us. So we really focus on very small features.
Professor, I'd like to present the certificate. Your lectures were very unique, especially how they connected theory to hardware, and I think everybody got a lot out of them. So
Thank you.